So today my project is about matrix search application on ranking list compatibilities. So basically we made a new dating match algorithms that will going to match people based on their ranking list on series of items, such as their favorite movie or favorite music. We're doing this by using the Kindle tau distance. And to increase the performance of this algorithm, we are going to apply the casting matrix tree to make it faster on search. The problem we found with existing dating app is that they usually give user a batch of profiles, but they don't tailor them down to the user's profiles. So you might get someone you're not interested at all. And psychology research has shown that similar people, they might have more successful relationships. And there's also some questionnaire methods that's available, but they're not really used by dating apps. They're mostly used by the old-fashioned dating agencies. And the kilometer distance is what we're going to use. They can measure the difference between two ranked lists. So why we're using a ranked list to measure the two people's compatibility. Another way to do so is by a scoring sheet. So you can allow users to score different interests, how much they like it. We don't choose that because we think a ranked list is more concise and more accurate. The example for this is like when you go get a new pair of glasses, they will ask you to compare two prescriptions instead of just let you rate each one. Because when there is a comparison, you tend to make more accurate choice. Another example is the political compass test. It's a test that will give you a different statement and ask you how much you agree with the statement. And at the end, they will tell you what's the most likely your political ideology is. I do those tests sometimes and I got different results every time because many times I choose close results but not exactly the same. But if there's a ranked list, I will think it will be more accurate and concise. And this is the distance metric definition. Basically, it's the distance that will satisfy all those properties. And the most common example of the distance metric is the Euclidean distance. And we can think any other distance, we can think it in the Euclidean distance way to solve the problems. And the Kindle tau distance is the distance we are going to use to measure the ranking list difference between two people. It measures the number of inversions in a list. And it's also a metric. So for example, we have two lists, ABCD and CDAB. We list all the pairs like AB, AC, AD, etc. And then in list 1, we can see A comes before C. However, in list 2, C comes before A. We call this a disagreement. There are totally 4 disagreements, so the Kindle tau distance is 4. And the normalized Kindle tau distance will basically use the Kindle tau distance over the total pairs, which is 4 over 6. And then we're going to apply the metric tree. Because now we have the distance, one really straightforward way to do this is we measure the distance between the query user and every other single user in the database. And then if the user is close to the query user, we'll return that user. However, this is really slow because we need to do every single user in the database. The time complexity of that is O of n. The way to solve this is by pre-computed information. We call them indexes. Here is one really simple way to do index. We take all the objects, we choose one object at random, we call that a root object, that's the red dot at the middle, and then we separate the rest of the object to 2 sets, the inner one and the outer one. And then we do this for every layer, so the inner one will also get separated to 2, and then when the query ball comes in, we'll see where the query ball lands. So if it's the red one, you only intersect with the outer one, we can skip the left one. And if it's the purple one, it does not intersect with anything, we can just skip the whole layer at all. This can decrease the time complexity of the algorithm dramatically. On theory, the time complexity of that is O of log n instead of O of n. And we test this implementation based on the code provided by that two source, and we test it based on different range of populations. The population ranging from 5 times 10 to the 3rd power all the way to 2.5 times 10 to the 6th power. And the length of the ranked list also range from 10 to 30. The R is the radius in the query. That means how similar the user want other people to be. It ranging from 0 to 0.17. We test this algorithm on the Intel CPU E5-2670. And this is our result. So we compare how efficient is our algorithm compared to the brute force one. So the z-axis there, the vertical axis there is how the lower the better. It's basically how we compare to the brute force. And we can see as the population size increase, it decreases. That means the larger the population size is, the more efficient our algorithm is. And then we can also see as R increase, the relative time also increase. And when the length of the linked list increase, it increased exponentially. And also we can see that the length equal to 30 is not shown here because when length equal to 30, there was not any result being queried when R is less than or equal to 0.17. So this implies that a shorter list is better for this application. And this is the result for the absolute time. We can see in 3 cases, it all increase when n funds increase sublinearly. That means in order to query more users, the time it takes will increase. This makes sense because you need to reach out to more users. But it increase sublinearly, that means if we double the user we want to query, the time it takes won't double. And we can also see that when the length is long, we didn't find that many objects because the R is less than or equal to 0.17, and we can see when length equal to 15, at most we'll only find 25 objects. But from this 3 graph, we can also see the result is in reasonable time. So even the worst case is we are querying 25 objects in about 12 seconds. That's a really reasonable time to on a dating app. That's basically 0.5 seconds per user. And we also tested how it scales across the population. The population means how many people is using the dating app. We can see that it's also sublinearly. That means if the user base double, the time it takes won't double. And it's also, you re-emphasize again, all the query is done by reasonable time. So since when the user doubled, the time does not double, this gives us the opportunity to update user's preference. So when in the traditional tree, it's not possible to update user's profile because that user's profile might only serve as a jump ball to the other 2 users there. However, since it does not increase, the time it takes does not double when the user base doubled, we can basically add a new profile to the database, and this would increase the population size. However, it won't be a big effect. We can see here, in the worst case, it will only increase from 3.5 seconds all the way to 4.7 seconds. And so that's basically our algorithm to this date, and we also do some future work planning. So the first one we're going to satisfy is the ring query. So in a ring query, instead of having a ball returned, you will have a ring. So the user will set a minimum distance they want. Every object that's less than that distance won't return in the return set. The benefit of that is you can satisfy incremental queries. So the first time the user can query all the objects between 0 and 0.1, and then 0.1 to 0.2, and 0.2 to 0.3 instead of query everything at once. Another benefit of the ring query is that it can return real interest object, because in the dating app settings, some people they might not want to date people that are exactly the same as them, so they might want to set a minimum difference they want to be. And we also plan to expand our algorithm to other use cases such as chemical matching. And in chemical matching, for example, we are querying all the chemicals that are similar to this one. We might not interested in this one because these 2 are really similar. You just remove a chlorine from that. However, this export site here, it might be the object that the researchers are interested in because it's similar, but it's not applicable. And so in conclusion, given reasonable parameters, our algorithm can query users' interest in practical time. And the dating app we propose is more tailoring down to users' profile instead of like existing apps that give user a bunch of profile. However, the effectiveness of this algorithm is not tested, and we are gonna leave this job for psychologists to do the work. And I thank you for University of Missouri providing the supercomputer for me, and thanks to my supervisor for supporting me for this project. And this is the reference. And the manuscript is available if you want to take a look.